Okay, this is our first atomic structure lecture, and it is not quite the first time we've talked about atomic structure because when we developed Avogadro's hypothesis and the mole concept, which is tied to equal volumes of two different gases at equal temperature and pressure, we get equal number of particles. So we've spent some time talking about development of atomic theory in terms of the gas laws and the mole concept. So many things are happening at the same time through history. So keeping with that, let's start like we've already talked about some of the same things, and then we're going to move on to the actual models of the atoms in this lecture that I'm holding you accountable for, developed through time. These are not going to be all the ones, but the ones we're going to cover today. In any case, first and foremost, as I've already discussed, before we got to John Dalton and some of the work that he did, and Gay-Lussac's and Amadeo Avogadro, we talked about the Greeks philosophers, and two of them talked about something called divisible and indivisible theory. So Democritus talked about an indivisible theory, so indivisible. Now, this indivisible theory that he talked about was in regard to that you cannot cut matter in half and keep doing so, a half of a half of a half, and still keep getting matter. His idea that at some point, if you cut matter into smaller pieces, okay, we would come up with something called atomos. Atomos is a Greek word for indivisible particle. Okay? So particle, we'll just keep it part. Okay, so his idea, just through thought, okay, there was no experimental evidence, obviously, about atoms, to 400 BC, but that was where the word atom came from, atomos. Okay, and again, it's cutting to smaller pieces. So you cut atoms into smaller components, you'd eventually come up with the particles that represent all different forms of matter. Now, Aristotle was held in much higher regard because of his teachers, and Aristotle's pretty much what he said went in terms of the Greek philosophers. Now, he came much later than Aristotle. I'm sorry, Aristotle came much later than Democritus, and he kind of just said, without any experimental evidence, obviously, that I don't agree with Democritus' idea of indivisible. I believe in the divisible theory. And the divisible theory, it was the idea if you take matter into smaller pieces, you would just get smaller pieces of matter. That there wasn't any particle that made up all different types of matter. There was just you take half of a half of a half, and you would keep getting smaller and smaller pieces of matter indefinitely. Okay, and that's why he called it divisible theory. Now, because of Aristotle's acclaim and his name and who taught him, okay, his ideas of the divisible theory went from before BC time all the way up until about the 1700s during Dalton's era. Okay, so that's where it began. And when we talk about atoms, it has its roots with the Greek philosophers and atomos. So let's go down to the first person who brings back up this idea of particles, and that's John Dalton. Now, if we bring back our PowerPoint that we looked at earlier this year, John Dalton, this is around early 1800s, and we talked about him already. He's striking a nice, cool pose I see there. And he did a lot of different things. He was a school teacher, but more importantly, he came up with this law of multiple proportions. But before we get to that, he had some basic called the 5 main points of Dalton's atomic theory. He was the first person to bring back atomos. Okay, and again, this I don't want you to write this down, but play from current slide. I want you to just look at this for a second. Way too big, but I want you to understand that that the things he was talking about were things we've already learned. Elements are made of tiny particles called atoms. All atoms of a given element are identical in masses. He thought atoms were the same because of masses. Didn't know about protons yet. We don't know this word about isotopes. We will though. The atoms of a given element are different from those of any other element. Didn't know how. He thought that was just mass at this time, him and a bunch of other people. We now know it's protons, but again, didn't know that yet. Atoms of one element can combine with atoms of another element to form compounds. A given compound always has the same relative numbers of types of elements. Okay, and atoms can't be created or divided into smaller pieces. Remember, this is the divisible theory. He's bringing back the idea that the smaller pieces of matter, or matter eventually, if you cut them into small pieces, you'll eventually come up with these particles called atoms. So therefore, this is a part of, you can't crush, you can't create, we're just going to interchange parts in terms of chemical reactions. Any case, we've talked about this at length. He was the first to bring back the atomic theory that there were atoms. And he brought back atomos using these five main points, and this was the modern atomic theory. Of course, it had a lot of holes and a lot of problems that we've already talked about, but I can't help but not mentioning this law of definite proportions. If you remember, we have carbon and oxygen. They didn't know about the chemical formulas, but they do know it made a different compound. So when you have the two or more different elements making more than one compound, the mass ratios are always whole numbers. There's a 3 to 4 ratio, it's just 3 to 8, and this led him to believe that there were particles. Okay, we talked about this. He was looking at data from gases and kept coming up in different ways, whole number differences of how these gases reacted. Okay, and if you remember, Gay-Lussac also looked at them. Okay, and Gay-Lussac came up with whole number ratio of gases when they reacted to each other. So there's a lot of evidence of these whole ratio differences that created the idea that this must be due to particles. Of course, Amadeo Avogadro, in his hypothesis that we've talked about ad nauseum, okay, let us figure out what was inside the box in terms of what the particles were in each seat, so to speak. And it led us, of course, starting off on this revolution, so to speak, of gas reactions, and of course reactions and balancing, everything we've talked about, and mole concept. Just going through this as we've already done. So, okay. So where are we left? Well, we're left with this person called J.J. Thompson. Before we get to him, we have to talk specifically what John Dalton did. Okay. Now, as I already talked about John Dalton, okay, his time period is about the early 1800s. I'm sorry, early 1700s. What did I say? I'm sorry, I've got myself all confused here. What did I say? Let me get this time period right. What did I say the time period was? Yeah, early 1700s should believe your first thought. So early 1700s, it's good to understand how the history of how things were developed to get them. So early 1700s. All right, so let's go back to this. So I don't know exactly when these things happened, but early 1800s. So 1800s early. Okay. Now he did a bunch of things. We have the law of Dalton's law of partial pressures, which we're still using in our labs and our quizzes. But he had the first model of an atom, and it wasn't that advanced. It was a circular sphere, and it was a solid sphere. Okay, so a solid sphere. Okay, and that was the atomic model. And it was based on just evidence that, you know, gases do take up some space and gases do apply a pressure, so it makes sense these smaller particles were solids, solid little spheres, entire. So this was his atomic model. And it was based on all the different results of his experiments that he did and other people did. He did a lot of taking other people's work, Antoine Lavoisier, Joseph Priestley, among many, to come up with these whole number ratios. But his crowning jewel, of course, was the modern atomic theory, and more importantly, the law of definite proportions, okay? And of course, from that, we developed the idea that atoms are existing because of these whole number ratios. And we should already understand how this led to Avogadro's hypothesis, Gay-Lussac's work, and eventually knowing what the actual chemical formula of compounds were, okay, and what was in each box, okay, through Gay-Lussac's work too. Okay, we've already been there. And we diverted into gas laws here and did all kinds of math, but now we're going back into the models. All right, so let's go back to J.J. Thompson.